Thank you, everyone, for coming and for moving and for waiting. I'll try to make it worth your while. It's really great to be here. A lot of friends and colleagues, and also people that I don't know, which is exciting. Hopefully, we'll have some new things to learn from each other. And so I'll be sharing today something between relevant background and a sprint through papers and things that we've learned in applying the ideas of computational mechanics to understanding neural networks. Like, how do they represent the world, and what emergent behaviors can we anticipate? So maybe I should say a word on comp mech. What is this thing? Computational mechanics, maybe a bad name, comes from something like statistical mechanics, but not static. The idea being like, what's at the core of understanding predictions? What are the ultimate limits of predicting the future from the past? What features of the past are required to predict the future as well as possible? And a lot of this work has been done over several decades by Jim Crutchfield and many colleagues, where really we weren't thinking about neural networks at all. In fact, we thought neural networks are unprincipled, and so we were doing a bit more of a principled thing. But obviously, neural networks have been working very well, and there's something to explain. So, so Adam's back here. I'll go ahead and just give the talk for us, but Adam, feel free to chime in if I'm saying something stupid. So Adam and I, and with many other colleagues that are here also, we started looking at kind of the simplest things of what if we applied some of these theoretical ideas for how you would represent the past well for the purpose of prediction. If you apply these to neural networks, we just got really lucky. It ended up working. So I wouldn't say that computational mechanics is kind of the full answer to interpretability, but it gave us a really good foothold that we're now building on, kind of whatever it takes to just figure this thing out. Motivational question here. Let's take a step back. The experiments are fun, the research is fun, but what does success look like? What would be required, what type of understanding would be required of the internal structure of a neural network, or whatever an AI is made of, or any intelligence really? What understanding is required to trust the behavior, right? I think it's complicated in that most intelligent things that we're aware of have a very similar architecture to us. Like other humans, other animals, if they behave a certain way, we can kind of map that onto, oh, well, this is probably what's going on inside. You have a pretty good guess because your architecture is like quite similar to theirs. Now with artificial neural networks, the architecture is so different, it behaves, sometimes very smart, sometimes not. But we don't have that type of mapping to do, right? So some people say that, well, it's not smart. It can't be smart. It's just a computer, right? It's just a physical thing that sometimes acts smart and sometimes doesn't. But I'd also like to remind people that we're also physical systems that sometimes act smart and sometimes don't. And it's really, if we don't have this link between internal structure and exhibited behavior, we don't have trust, right? So we somehow need to build up this whole fundamental science. We need to build up foundational understanding to be able to have any trust in moving forward into this thing that we're being thrust into, right? This AGI paradigm. So a little bit more operationally, because this is maybe daunting, a little bit more operationally, we can just take the neural network on its own terms and say, what's the nature of computation in this thing? Is it just like through training, there's like some hidden Boolean circuits or something like that? Well, I'll describe how that's not the answer, but we're able to get at this, and this is kind of going to be a motivating question of what's even the nature of computation in these devices. So the plan for this talk is motivated basically by these 4 questions. It's a bit long, but I'll just read them for you. So first, what computational structure are we building into large language models when we train them on next token prediction? So next token prediction on its surface doesn't seem that sophisticated. Maybe analogously, procreating doesn't seem that sophisticated. What can come of these types of functions, specifically next token prediction? The answer will be something about not only that the neural network creates a world model, but it actually, what it learns to do, it effectively learns to learn. It learns how to do Bayesian updating over the latent states of a world model as it moves through context during inference, right? So this is what we find here. And then this has a natural kind of consistency with, if you're doing Bayesian updating in context, then you should kind of reduce uncertainty. So there's a natural relationship with in-context learning, at least in distribution, and then it gets a little fuzzy outside of that. But if it's Bayesian updating, that sounds recurrent. So how the heck do transformers do that? Because they're these feed-forward networks. We were confused by this even when we figured out these other parts. And so I'll say a bit about how attention MLPs can actually implement Bayesian updating for this belief geometry. And then finally, this kind of weird other part. What's the fundamental nature of computational neural networks? What model of computation should we be thinking about when trying to make sense of these systems? I said earlier, is it like some hidden Boolean circuits or something? Well, maybe that was over simplistic, but the answer is also maybe still surprising, that we end up finding that the nature of computation is somehow more akin actually to quantum computation, or sometimes even beyond what can be done there, effectively because neural networks have access to this real vector space, right? So you can represent things non-orthogonally and on purpose, right? Sometimes we think of SAEs as everything wants to be orthogonal. Well, why should things want to be orthogonal? Sometimes if different histories induce similar predictions about the future, then you should encode those as non-orthogonal, and that means that you can also take advantage of certain things that people have associated with like a quantum advantage. So that's kind of a funny twist, and also a bit ironic because we named ourselves Simplex, and these belief states are now outside of the Simplex. So we're learning. That's good. Okay, so here's the bullet point answers to that plan. Just to reiterate, I'll say this a few times in different versions, so hopefully you come away with something from this talk. So the plan is to show you that pre-training induces belief geometry, that even kind of a simpler statement, pre-training induces this in-context learning, just kind of a behavioral thing. Transformers learn how to Bayesian update, and neural networks leverage this post-classical world model. And then if there's time, I'd like to give a little bit of a look ahead. We've had some initial success in these research things, which has been fun. We have now more of a line of sight to like, how does this engage with ideas of actually breaking down an LLM? How does this engage with AI safety? So I'll say a little bit about where our head's at with our agenda and projects we're excited for. So we'll start with this. Oh yeah, okay. Okay, so this question again. What computational structure are we building into neural networks when we pre-train them on next token prediction? I assume you guys have a concept of what this question is even asking, that we have strings of tokens, we're doing log loss on the next token given some context. What's inside the model, right? People have argued about this kind of endlessly on Twitter. There's all sorts of suggestions. One suggestion that I resonate with is from this guy, ILIAD, who many of you will know of. And so ILIAD's idea here is that predicting the next token well means that you understand the underlying reality that led to the creation of that token. So I mostly agree. This is something like doing well on pre-training means you get a world model. But how do we operationalize this? Can we set something up that's falsifiable so that this claim's true and something else is not? Well, predicting the next token, I think we have some idea of what that means. Understand maybe something about a world model, underlying reality. Maybe underlying reality is about a world model, and then what does it mean to understand that? So, okay, how can we operationalize this? What if we knew the structure of the training data, right? So what if we just took this simple three-state hidden Markov model and said, this is what we're going to train on. We're going to do next token pre-training on data that comes from here, just A's, B's, and C tokens. It's non-Markovian because this is a hidden Markov model, not a Markov model. If you train on this and you take this idea seriously, what happens when you look inside the black box? So you might think, well, okay, if it learns this thing, maybe it'll learn something like, it'll somehow encode the transition probabilities, the fact that there's 3 states. But actually, we're going to kind of refine this proposal that, yeah, there will be something like a world model, but more specifically, predicting the next token will means that you perform Bayesian updating over the latent states of a generative world model as you observe more context during inference. So it would be more like updating your probability distribution over which of these latent states you're in as you're observing these tokens. And so what that should look like is actually you open up the black box and you see this kind of crazy fractal. And indeed, we find that over the course of training, there's a linear map from the neural activation space. For the case of a transformer, it's in the residual stream. Over the course of training, this geometry seems to emerge. So that's pretty promising.
What are the points in the simplex here? Like samples,
yeah, thanks.
Samples from the latent space?
Thanks. This is a great question. So this is this true simplex where each point corresponds to a probability distribution over the states of this generator here. And a probability distribution over these hidden states corresponds to a probability density over all possible futures. Mm-hmm. And what does it mean that this thing is inside? Well, for any given context, it induces some point in this high-dimensional activation space. And so that's like one point here. And then the claim is that a different context will embed itself also into this high-dimensional space, but it has a geometric relationship to this other context. And all the different contexts have a very particular geometric relationship to each other, which has to do with in what ways do those contexts make similar or dissimilar predictions about the future.
I guess my question is like specifically, how do you generate this simplex?
This one here, or this one?
Yeah, or any of the ones on the...
Yeah, so I'll speak to that in more detail. I think the next few slides should show, and if not, then I'll follow up. Yeah.
Does that emergence remain stable across like different random seeds as well as different optimizers? So I think that one used SGD.
Mm-hmm.
I was wondering if like you tried using Atom to see if like optimizer choices affect that, and if that's stable across random seeds.
Yeah, I mean definitely we find this sort of stuff with Atom, and most things that we've tried, it basically just works. There's plenty of open questions in detail, but I'd say that most things that we've tried, that this geometry appears somewhere across the layers of the network. The specific ways in which it appears will depend on the architecture, but I'm not aware of it depending on like the learning algorithm.
Okay.
Yeah.
A couple of questions. So this is obviously a very simplified setting.
Mm-hmm.
Do you have any handle on the external validity of this approach? Like, how much should we believe this is true about like language models, for instance?
Yeah, we definitely weren't sure at first. I have much more optimism about it now, in part because of what I'll talk about at the end, that if we're talking about what's the minimal generative model for like everything on the internet, it's huge, right? And there's just not even enough dimensions to fit that, so this story wouldn't extrapolate, it would have to break. So one thought is like maybe we can see how it breaks and move from there. That I think will be part of the answer. But also, we're seeing how these belief structures factor in these ways where things can happen in parallel, which means it can be much smaller dimensionality than if you had to represent everything in like one simplex.
And just one brief follow-up. If you took just this setting, but you increased the number of states, but you kept kind of a fully connected matrix, do you have a handle on how much data you need to learn that? I assume it's going to be exponential the number of states, but not sure. Or...
That sounds plausible, but I don't know. Yeah.
So you're really relying on this factorization to move to more states?
That's what gives me optimism, and something about that the neural network is working at all, that it's learning at all. It has some way to represent this, so of course there's a chance that we fail some way along the line, but so far it seems like there's things to check.
If the transformer learned to do the prediction task well, is there any way it would not produce the theoretical prediction in the end? Like, doesn't it have to? It has to do that.
It's a great question. One thing is, after we came up with this result, we thought, like after you come up with a great result, and in hindsight it's kind of trivial. We worried it might be that. And then we ran this hackathon, and a lot of great people did stuff over 4 days. Rick Goldstein, who's maybe here, did a project where he, by hand, wrote down the weights of a transformer that exactly solves, actually not this task, but a different random XOR task. It exactly gets it right. And the activations don't map to the anticipated belief geometry. So it's like, in a way, interesting that it didn't have to be this way. So it's actually a less trivial result, that there's something about an inductive bias that maybe this is something like, this is the robust thing to do. So it's like, in a way, both are good and bad things. It's like, it's a non-trivial result. It didn't have to be this way, but we also don't exactly know where the limits are in terms of when it does and doesn't do this. But it seems like this is pretty robust.
So it is possible to predict a system well, but not discover the causal states.
Or not represent them in this linear fashion.
Or not like kind of, okay. Oh, I see.
Yeah. Like there are different encodings, perhaps.
Thank you.
Yeah.
It sounds to me like it's really about the linearity of the embedding of the mixed states. Because as you said, the causal states were still there in the transformer. It's just they were not linearly independent.
Yeah, I mean, there's different parts of the recipe. Like, if it was a recurrent network, then in some sense, the belief states, the causal states would have to be there. For a transformer, even that's not totally clear. And then there's the stronger claim that also these belief states are linearly represented. There's a linear map from activations to this thing. So I should probably go ahead, unless it's real quick.
Small clarification.
Yeah.
Like, so if you're like on the top of the triangle there, that means it's like 100% you're in state S1?
Yeah.
Okay.
Yeah, that's right. So this is this probability simplex. That's like, this would be for sure I'm in this state, for sure I'm in this state. And generically, even when you're like as synchronized as you can be, you won't necessarily be on the edges of that. But you're right about what that means. And the next few slides should hopefully make this more clear for everyone too. So what we did is let's operationalize this thing. Even if we know ground truth, even if it's very simple, can we say what's inside the neural network, right? And so we use these hidden Markov models. It turns out the story isn't limited to the hidden Markov model setting, but it's a very useful type of example to look at. So here's another HMM, which is just this 0-1 random process. And what's this thing like? Well, what's really nice about this is that it's a linear model. It's a linear model over the latents. And that's actually quite general. Like if you think of quantum mechanics, for example, like everything's linear. This also is linear in the sense of you can construct the probability over a sequence of tokens. So the probability of some word of length L can be obtained just by having the initial distribution over this thing and then multiplying, just matrix multiplication of these transition matrices. So these are, in this case, these substochastic transition matrices where every element corresponds to a conditional joint probability of what's the probability of seeing the next token X and moving to the next hidden state S prime, given that I was in the latent state S, right? So every element of this guy says that, and so it allows you to calculate these probabilities, which is real nice. And so then, okay, what if I'm trying to predict this thing? So even if I know this is what the world is like, if I'm trying to, I go to sleep at night and I wake up and I just start observing, it's like you're at the beginning context. You just start observing outputs from this non-Markovian world. The best you could do to make predictions would be to have kind of the correct probability distribution over the latents, right? So there's a metadynamic. So this is like this generative dynamic, but then there's also this metadynamic of how my beliefs would move as I observe more tokens. And that's what this is showing. There's this graphical structure of this mixed state presentation, this belief metadynamic of, let's say I start in the stationary distribution. If I observe a 1, I go to a new distribution over these states, which is now just a state here. It's a belief state. Right? And in general, the recurrent structure will not look like this. It happens to look the same here because of a property called unifilarity, but in general, this can be some like kind of infinite state thing. So we go from this graphical structure to this also graphical structure of how beliefs update. But it's not just a graphical structure. There's implicit in this, there's also a geometric embedding of these states. so because every one of these states corresponds to a distribution over that original model, which means that it lives in the probability simplex over those original generator states, right? So there were 3 generator states. So here you can see this 2 simplex in 3D. Basically, it's the probability of each of the latent states, but probability is normalized, which takes you to this plane, right? And so every one of these belief states is naturally embedded in this probability simplex over the generator states. And this is basically just showing how the updated probability, this is basically just Bayes' rule written with linear algebra, is the updated distribution over the states and dividing by the normalization. So let's think about this a little bit. We can really utilize this linear latent model to say, what is the probability distribution over the future of arbitrary length given some past? Well, I can just say that's just this conditional I can write as the joint divided by the marginal. It's the joint probability of that context, that word, that sequence of tokens, and then also the future divided by the probability of that specific sequence, right? And then if I group these terms here, I recognize that every word, every sequence of tokens, it induces some vector here, right, in some vector space, that any words that induce the same vector, they can't affect the future differently, right? So there's this natural partitioning, this natural coarse graining of histories into the same causal state, if you will, belief state. But it also tells us a little bit more, that if 2 histories induce kind of nearby vectors, then it can't affect the future very differently. So again, we're seeing a little bit of how this geometric picture is coming in. It's not just same or different. It's if you're nearby, you're going to make similar predictions about the future. And this also helps you to see a little bit how this extends beyond hidden Markov models to any linear latent model. Okay, so then how are we going to go about finding this in, let's say, a transformer? So this is probably something like a familiar picture that we have this thing we call the residual stream, which is just this vector space that goes through the layers, right? And then you're going to have these repeating layers of attention, which shuffles information across context position, and the MLP, the feed-forward network, which only computes on the information locally. So repeat this stuff. So for any context is going to induce some point in this high-dimensional activation space. This is obviously a cartoon. And then the claim, and what we find, is that there's a linear map then from this activation space to the anticipated geometry. So it's just kind of a cartoon schematic of that. And it turns out also you can just do PCA, and that also seems to work for finding the belief geometry in most cases.
Oh, sorry, can I ask a quick question?
Mm-hmm.
You said that, I mean, it's non-chaotic, so if you're in this,
I didn't say it's non-chaotic.
we said if you're nearby in this space, then you sort of stay nearby as you evolve the thing forward.
No, sorry, that's not what I meant to say. Thanks for clarifying that. So predictions about the future are similar, but in a way there's like only so similar you can be because a process like this has an entropy rate, a non-zero entropy rate. So future predictions will diverge, but still some histories will make more similar predictions than others. Like maybe that's even only just like a short time horizon. So for example, like I can be in, pick your favorite distribution over this thing, and then make some perturbation to that. In the near term, you would make similar predictions, right? But as you go into asymptotically long time, they would each kind of independently evolve to the stationary distribution if you weren't tracking things. So yeah. So it's kind of like if you're nearby at some point in the simplex, if your observation is
they would evolve towards the stationary distribution. They would.
Well, if you're not tracking the specific token, if you're you're tracking the specific tokens, then it'll kind of bounce around this attractive structure. And you're totally right that in fact these are effectively chaotic systems, so their trajectories will diverge. But there's despite that kind of as similar as possible predictions. So not everything's predictable about the future, right? To start, but you want to predict everything that is predictable, and so to do that, you take into account all of history. And if different histories tell you similar things, then even over the whatever horizon you have, there's some overlap there.
Okay, thank you.
Yeah. Yeah.
Hey, so with regard to the chaoticity of this attractor, Alexander Jurgens, who's behind me, has done some work on basically deriving was it a derivation of something like the Kaplan-York conjecture that though each of these maps is contractive and has like a negative Lyapunov exponent due to the stochastic nature of it, you have sort of a fractal dimension of this attractor that you can calculate.
You have a non-zero dimension.
Non-zero dimension.
Yeah. Maybe Alex can give a talk on it. Would be nice. Plenty of slots. Yeah, there's been like all sorts of really nice work on this from Sarah Marzin, Alex Jurgens, and like you can really get into the details here. But yeah, hopefully I'm conveying at least the high level picture of how some of this stuff works out. If this is what the world is like, then we anticipate this is kind of, in a sense, the optimal geometric belief structure, and then we end up finding that in neural networks, whatever the architecture. Then this was this NeurIPS paper from 2024 that Adam did all sorts of careful controls to make sure we weren't fooling ourselves, that we're not just getting this geometry by going from like high dimensions to low dimensions or something like that. But I encourage you to look at the paper if you're interested. One other point I want to make on this is that the prediction is more than just the next token, even though we were explicitly just training on the next token prediction, right? So here's an example of this random XOR process that I mentioned earlier that someone else also worked on and wrote the weights down. So this is like you flip a coin, and then the next token is just the XOR operation of the last two. But actually you don't know the phase. And so to disambiguate, to figure out what's the correct phase, and to predict as well as possible, you'll go through these kind of different motifs of resolving ambiguity. And it's kind of interesting that you kind of have to resolve this ambiguity before you can even get a chance to resolve this one. So there's some interesting structure there. And so this thing happens to have 36 belief states. And crucially, many of these belief states have exactly the same probability distribution over the next token. But despite that, so this thing lives in a 4 simplex. We're just projecting it to 2 for visualization. And it turns out that transformers and whatever neural net, they learn this thing. They choose to distinguish these belief states, even if it has literally the exact same next token distribution. So that's quite interesting in terms of that the networks seem to be doing more than we explicitly asked for. And then the final point I want to make on this is that the representation ends up, for many of these processes, the representation ends up being spread across the layers. So it's not just like it exists in one layer, but for these processes, it happens to be in the final residual position and spread across the layers. Yeah.
When you say they have the same next token prediction, you mean the same like very next, but they're going to use for
Yeah, exactly. And so it's the same distribution over the next token, but eventually down one there's a difference in what will be the next token, right? And so for that reason, the network chooses to distinguish these things. Otherwise, effectively, it might make the wrong next token prediction later down the line. Is kind of an intuitive way to think about this.
Like the way these are represented in this residual stream, is the arrangement exactly the one you predict? Like not only are they distinct, they're also like arranged like the one that's left and the one that's right and the one that's up and down, the way that you expected from the map?
Yeah, so yes, exactly what we predicted up to like linear invariance, effectively. You can kind of just do PCA and then you're making some less assumptions and it's also the same geometry. There still seems like there's some flexibility, and something that's still not clear to me is like, is the thing there up to like effectively rotations, or is there like stretching and permutations? And I'm not actually sure about that. But it's like quite there. Yeah. So.
There's some questions back here.
Sure.
Oh, I was just going to ask. So I'm assuming if two belief states would never diverge like over infinite time,
Yeah.
what they would predict, then they wouldn't be distinguished by the model?
That's true, but they would also be the same belief state.
Maybe.
Yeah, I mean, if different contexts induce the same probability density over all futures, then they are kind of by definition the same. Well, they're the same causal state in that case, which would merge that. Yeah.
That sort of example, you said that how many belief states it has?
Oh, that was 36 in that random XOR thing.
Yeah, but where does this number come from?
I mean, so sometimes it's finite and sometimes it's not, which is kind of interesting. My clicker's not working great here, but right. So in this case, there's these 36, which basically, because this thing's unifilar, you can think of it. That's effectively a word for like deterministic automata.
Okay.
If you know which hidden state you're in and you know the next symbol, then it determines what next hidden state you go to.
Yeah.
And when you have a generative structure like that, then there's a finite number of recurrent components in this thing. When you have non-unifilarity, which is like non-deterministic automata, then it's like you're folding in Bayes' rule over and over, and you end up getting this fractal structure for that reason.
Okay.
Does that make sense? Yeah. Yeah. So, I notice I'm lacking my drink, which I put here. So if anyone sees it. Also, I'm lacking my timer. So what time is it right now? I know we started at 1:53.
There's a clock at the back.
Oh, candy. Okay.
32 minutes left.
Cool. That sounds good. Great. So I think we can do this. We'll give like 10 minutes to each, maybe. Okay. So then this was about the internal structure of this Bayesian belief updating over latence. There's this other thing which is consistent with that, and in a way even simpler, just about the behavior. That if you're doing Bayesian updating, you should be reducing entropy in context. So that has something to do with in-context learning. And to see how that arises, at least in the in-distribution case, well, we can say, well, what's this next token prediction loss? It's this cross entropy loss, right? That maybe this is the more familiar way to put it. That we're saying there's some parameters theta. This is the weights and biases of your model. This is my cartoon of a deep neural network. You move through the layers and you move through context positions, right? So every cross here can be thought of as some kind of high-dimensional vector space. And then when you're learning, you're getting these token sequences according to some like ground truth distribution. There's like some Platonic realm of where you draw your sequences from. Let's call that Q. That's the ground truth that you're training on. And at any point of training, initialization or down the line, whatever, there's some weights and biases, or some weight setting theta, and there's a probability distribution over the next token given that context, right? So these two different distributions going on, the ground truth Q and this P theta, and cross entropy loss, you can think you accumulate from all the positions of minus log of the probability that the model predicts of the next token given the past, and then you weight those according to how often you actually see it, so according to the ground truth, right? So this is just cross entropy for each position, or you can also write it as cross entropy for the joint. Well, we know that cross entropy is minimized by just entropy itself, by Shannon entropy. And so if the model learns well, and you're minimizing this, doing a good job at minimizing this cross entropy, then you're going to get just minus Q log Q, right? Just Shannon entropy, which then decomposes this way to say there's this, what we call myopic entropy, the minus log of the probability of the next token given the past, which in general is decreasing. So especially for a stationary stochastic process, this thing's definitely non-increasing. And at least in distribution, this ends up allowing us to predict effectively exactly what the in-context loss looks like. So recall again, we have these different generative structures, and for each of them, they have this mixed state presentation. This is just the graphical structure of that belief metadynamic. And then that implies then this myopic entropy rate. And then over the course of training, which is the colors going from light to dark, this is the in-context loss of a model that we train on it. And this was worked together with Henry, Eric, and Adam that are all here. and I should also say for the last work was together with Sarah, Alexander, who are all here. I don't know if Lucas is here. So anyway, there's this behavioral thing that we anticipate in terms of in-context loss. And one quick kind of mathy note I want to make is that when you have a few coins, basically, if you have non-ergodic processes, even if they're very simple, and you train on these non-ergodic processes, that is sufficient to create power law decay on the in-context loss. Usually people associate that with more sophisticated grammars, like instead of regular grammars, you would have some context-free or context-sensitive, which indeed would lead to power law decay of the loss as you move through context. But I think it's interesting that also just training on many different ergodic components also does this. So maybe I should say a bit of a word of what's this ergodic thing. The stuff that I showed before was like, this HMM is what the world is like. But really, when we're training on like data from the internet, there's kind of this whole hierarchy of different types of models we might be sampling from, right? So you might think you have to figure out like what language am I speaking, what genre, what author, what mood, and all this. And you can think of those as all kind of their own ergodic component in a way. And so then the model, when it's doing inference, it not only needs to figure out which of the hidden states am I in, which latent state am I in that ergodic component, but moreover, which ergodic component am I even in? So there's a much grander task, and just that non-ergodic part leads to this power law decay, which is interesting. So there's some interesting transient stuff we get, but I don't have time to talk about it. You end up seeing, and again, the whole story we've been talking about up to this point actually had nothing really to do with transformers. It was really just this model agnostic thing about predicting well. So whether you're looking at transformers or RNNs, LSTMs, you end up getting that the model learns to do this in-context learning and distribution. We even find, this was some work that Eric was doing, we even find these type of like phase transition things, this kind of grokking thing. But obviously this wasn't about induction heads. And then the important point though is that even though every architecture does this, it's doing the kind of correct Bayesian updating in distribution, the mechanisms that it learns, given what it has, what the architecture provides, the mechanisms it learns to do that in-context learning and distribution implies how it's going to generalize, right? So that motivates looking more mechanistically, well, how the heck does, say, a transformer implement something like Bayesian updating? And so that's the subject of the next point here. How is it that transformers learn to do this effectively Bayesian updating? I've already mentioned this kind of apparent conflict that belief states naturally you would think of updating iteratively by Bayesian updating. Transformers are inherently parallel, feed forward. So what's going on? So we were working with this great researcher, Mateusz, who is a maths scholar, and Mateusz was doing kind of like mech interp sort of work, mech interp style work of looking inside, what are the attention patterns and things like that. And we were trying to map between looking at the model internals in great detail and mapping that onto our kind of high-level theory. And it turned out to be this really great interaction. So this is, again, we just use this MES3 process, this three-state HMM. There's this belief state geometry that basically I already showed you before. I think this is for a slightly different parameter setting of the model, of the HMM. And yeah, okay, so at some point the model is going to learn this thing. But what happens kind of at intermediate layers, let's say like after attention but before the NLP? We end up finding that the model learns these other fractal structures, just in this case looks like this Sierpinski gasket, that we can also anticipate, but it's different than this final thing. So what's going on here? Okay. So here's the cartoon of what I was saying that Adam nicely put together for us. So if you're just trying to do Bayesian updating, you have a belief state, you take some observation, you update, you have a new observation, you update, right? Well, transformers can't do this. Attention's parallel, so at whatever position you're at, you're going to kind of effectively independently take information from every position before you. So you can think, at least at the first layer, you're just going to be taking everything in kind of independently, maybe in the best way possible. But what is the best way possible? What does that mean? And so when we kind of tie these ideas together, we kind of wed the math of Bayesian updating with the architectural constraints. We're able to anticipate in great detail, like what's the embedding, what's the embedding, the attention pattern, these intermediate representations, and the final representations. So the final representation, to remind you something like what's the probability distribution over the latent state at the destination position, if we're thinking of context position, destination position, given all the tokens up to that point. This is kind of like if you take all of history into account correctly. Well, what if you can only take the information from past tokens in independently? Well, then a natural thing to do would say update the probability distribution from the stationary distribution, say like, well, what's the probability distribution over the latents at the destination induced by the source being this particular token excess. And then you can kind of think of summing these differences in a simplex effectively, and what would that give? And then you can write that down in terms of the linear algebra that we had for our linear latent model, and that immediately gives the geometry, right? So we were writing down probability distributions, but if you just write it down with the linear algebra, these are all vectors, and these also are vectors. And so it gives a prediction for what the intermediate, this is again post-attention, but before the NLP, we anticipate these geometric structures, which are of course different than the kind of final theoretical thing. And then when we train the model, this is just PCA at these different points in the model. It does pretty good. I mean, it's not perfect, like you can see here. I think just because it wasn't a big enough model, effectively. But it's pretty good. It's even hard to tell sometimes which one's the theory and which one's the experiment. So pretty neat that we're able to predict things at this level of detail. So how did this work? Well, I kind of alluded to this, but basically we can write down these equations where on one side we write down things about the architecture. This is like the embedding. This is the attention, the OV vector. So this is architectural stuff. And on the right is the linear algebra of what you want the architecture to be doing. This creates like a self-consistency, a set of equations that, if they're self-consistent, they predict what the architectural things are, right? And, okay, we end up finding there's the spectral decomposition, which comes into the story. But as I said already, we can anticipate the embeddings, which are these circles. We can anticipate the OV vectors, and that all bears out. We can anticipate the attention pattern, and the whole thing ends up being just this algorithm in the simplex of how the transformer's taking in information from past positions. Yeah, Alec.
So the constrained belief states that you found in the system or in the residual stream, those are for a single layer of attention?
Yes.
Yes.
Yeah, so you can think of, there should be a similar story at any layer. It's going to be taking in, at that layer, things independently from the different positions. And then you can ask at that layer, what would be like the best thing to bring in? But this was like quite simple in that a single attention layer is actually enough to figure out MES3. For other processes, you would need to do larger architectures.
So you anticipate, what's the story when you add additional layers with regard to these constrained belief states?
I anticipate that like some of the story works out, some of it's going to be easy to extrapolate, and some not. That's just like a great research project for someone to do, and we haven't done it. It's a very Toya setting that we've looked at, but it like hints at, hey, this kind of framing can work. So I encourage people to do it if they're interested. All right. So one of the things we get from this is it turns out that the attention heads are kind of implementing a spectral algorithm. So like the transition matrix for the generator, right, this kind of ground truth thing, you can think of the spectral decomposition of that thing, and the attention heads are implementing a spectral algorithm in terms of incorporating past information effectively according to that eigenvalue, according to that spectral projection operator. So one of the things this tells us is that, like even in the simple MES3 process, you can change the process, the parameters of the stochastic process, such that suddenly that matrix for the generator has negative eigenvalues. And then suddenly, you're going to need at least 2 attention heads for the transformer to be able to learn that thing, which is exactly what we end up finding, that as you're changing the parameters of the stochastic process, suddenly, if you get to a negative eigenvalue, you need at least 2 attention heads because the attention wants to do this spectral implementation of your constrained belief update algorithm. And again, in this case, we can anticipate all these things. And why 2? Because attention has to be non-negative, but if you have a negative eigenvalue, you want to pay attention in this kind of oscillatory fashion. And so 2 attention heads allow you to have both the positive and negative contributions to that. Right. So this was a really fun project. There's, I think a natural question of like, well, it's very toy, how does it scale? But I think it's, I'm biased, but like the best version of mech-interp I can think of, I feel like mech-interp is a good style of doing things. And hopefully we can scale that up. Okay, so we now have this part about neural networks leveraging post-classical world models. And so I think, I still have some time actually, so it's okay. What's going on here? Well, we already noticed, even in the cases we were looking at, let's take that MES3 example where there's that 2 simplex, all the fractal geometry. We already saw in that case that the neural network was utilizing non-orthogonality, right? If different contexts induced similar predictions about the future, then it would embed those contexts non-orthogonally to indicate it's similar in this way and not in this way, right? And you would use the different dimensions to say in all the different ways that it can be meaningfully different. So we already saw that neural networks utilize non-orthogonality. And then I was thinking about this after we had this kind of initial success with the NERPS paper. I used to work on this kind of foundations of physics quantum stuff of if you had access to quantum memory instead of classical, turns out that you can use far fewer dimensions with your quantum memory, with your qubits, than you would otherwise classically need to predict the future. Why is that? Well, in most of the examples that were worked out, it was really just that quantum systems can take advantage of effectively a continuous vector space. That the pure states of a qubit can be 0 or 1 or whatever linear combination of that. But neural networks, so they're operating in this real vector space. So I was excited and telling Adam, like, these things are going to learn these quantum representations. It's crazy. And then Adam was like, somehow believed in me, and I was grateful for that. Turns out they do. It's real. So it's this kind of crazy thing. So neural networks transcend the classical paradigm of computation, and we have this nice paper together with Tom, who's here, that neural networks leverage nominally quantum and post-quantum representations. And let me kind of zoom out to tell you the story as I see it here. This isn't really about classical versus quantum. It's much more about the paradigms that we think about in classical computation and quantum computation. The paradigm that we think about in classical computation, you have these memory states that are mutually exclusive. It's either this memory or it's that memory. It comes down to this coarse graining of your physical state space. Well, okay, in quantum, you can have not just 0 and 1, you can have, not just 0 or 1, you can have 0 plus 1. Importantly, that's different from 0 minus 1, but you have this whole continuum of pure states of certainty. And then the convex hole in that, so this is like the block sphere for a qubit. And then there's even more general, just like convex structures that would go beyond what you can represent with a finite dimensional Hilbert space. And people in the foundations of physics talk about these generalized probabilistic theories, GPTs. Then it's kind of cute. It turns out that GPTs learn GPTs. But also, other neural networks also learn GPTs. So here's kind of the workflow here, is that there's some stochastic process that you're training on. This should probably be called Q to be consistent from my other thing. There's some stochastic process that you're training on. It produces some token sequences that you would train on, and then you'd have neural activations once your neural network has learned that. And then the claim is that there's a linear map, maybe affine, maybe linear, from the activation space to this anticipated belief geometry. So you just short circuit here. From the process itself, you can anticipate a belief geometry when you can when a quantum framework allows you to use many fewer dimensions, basically the model is going to learn that. And so just to kind of hint at some relevant theory work that's been done here, quite recently, well, some of the work like on this side is quite old, but quite recently this whole thing has been figured out, that you can think of classical quantum and post-quantum, people do this in literature, as the set of processes that can be generated by a finite dimensional hidden Markov model, a finite number of hidden states. That's different from the class of processes, even though we're just trying to do like classical tokens, right? Correlated random variables. If you had access to a quantum memory, so with a finite dimensional Hilbert space, what are those classical stochastic processes you can generate? And then there's an even more general class of these generalized probabilistic theories that if you just give yourself a very general latent space, finite dimensional latent space, and you insist on a linear model over that latent space, what's the class of classical stochastic processes you can generate? So these are three distinct classes. But the discovered advantage that differentiates these, again, is just about effectively utilizing continuity in the real vector space. And then, of course, neural networks can do that. So what does this look like? So if you're just trying to generate tokens and you have a qubit, you can imagine I have some belief state, which is like a point in this block sphere, which represents like my belief about the state of a single qubit. And then as I observe more tokens, which would be like this POVM if you know quantum, but like as I do different general measurements to my quantum system, it would update my belief. The same way that I would have moved through the simplex, I could move through, say, the block sphere. And so you can think of very much like belief updating via these Krauss operators. There's all sorts of ways of doing it. It's completely analogous. And then over the course of training, kind of similar to the picture you saw before, there it is, this beautiful process that Tom helped us to think up. Originally we were calling this Tom Quantum, and then Tom's on the paper, so we can call it that, so it's block walk, whatever. But it's kind of a beautiful thing that one of the things to look at is as validation loss goes down, basically the Euclidean distance to the anticipated geometry also goes down. So, and we tested other kind of hypothetical belief geometries that it didn't learn. Like it learned the quantum thing and didn't learn the classical thing. And then, so you can have classical, quantum, post-quantum, and there's also a sense of universality that whatever neural network you're using, as long as you're pre-training, if your objective is to predict the next token given the past, there's this universality that any architecture wants to learn this geometry, just whatever is kind of the simplest geometry to represent the thing. And, right, so okay, maybe, yeah, some questions on this, yeah.
So there are processes that are outside hidden Markov models, right?
Yeah.
And what you're saying is that a system that can learn those processes is also better at learning hidden Markov models, right? Because is that what you're saying?
It's not what I think I want to say.
Okay.
So maybe you're saying like there's things beyond regular grammars that you might want to learn, like with pushdown and top-down, whatever.
Maybe I'll take us offline.
Okay.
I'm struggling with it.
Okay.
No, it's a great talk.
Yeah, thank you.
There's a
yeah.
question here.
Oh, can you give an example of a problem that would require infinitely many orthogonal states in classical memory, but finitely many in GPT?
Yeah, you're asking for an example?
Yes, please.
Yeah, there is an example in the paper where we've basically just taken from the literature. There's a paper by Finitza just from last year where they did that, and also Tom came up with this example. Tom, do you want to try to describe this in words?
I mean, I came up with it in a jet-lag fever dream on the way back from ILIAD last year.
Yeah. Hey, ILIAD's good for something.
Yeah, I mean, essentially you have 4 different symbols you can observe, and depending if you see like X, Y, Z, or W, you move up or down or left or right in the block sphere, but the amount you move is based on your current position. And so then you get this kind of like fractal-like structure, which if you try to do it as like classical states, there's just no finite way of doing it. Because it's, you're playing your probabilities in a slightly different way to play with H-RAM states.
Yeah. I like roughly sometimes think about it as like if you'd like to do something like rotations, it helps to use.
Yeah, actually, if you go back to the slide where you have the Krauss operators. Yeah, so one way to think about it, right, is classically your update rule is you have a state and then you act it with some stochastic matrix, right? So you have a very constrained structure here. You can think about your row as, I mean, you can put it into vectorized form, and then these Krauss operators act on that as a linear transformation as well. But those don't have to satisfy the same constraints as a stochastic matrix. So you have a more general set of transformations that are available to you.
Like some like the complex solutions.
Yeah, and then PHM just has basically as long as it's statistically valid, the A matrix.
Yeah. And I'll make one other comment on this, both to not drive Tom crazy and also to not mislead you guys, that there's still like something that's genuinely quantum that exists for quantum systems, but it's not this continuity of vector space. The quantum advantage is when you have many quantum subsystems. When they compose, you get an exponentially large latent space. And when you have something like that, like you want to break RSA encryption, then a neural net's not going to be sufficient. So that was a bit of a relief to me, and also it's kind of interesting that there's also that discrepancy. Yeah.
Should I think of this as, totally naive question, should I think of this as in any way at all related to other talk about superposition in neural networks?
Yeah, it's very tempting. Maybe no. Yeah, I'd suggest no. Their superposition, maybe something about non-orthogonality, but yeah, I don't know, just better to keep it separate. Yeah.
Yeah, so sometimes these quantum representations can represent things in finitely many dimensions that in classical systems would take infinitely many.
Yeah.
But sometimes you can do both in finite dimensions.
Yes.
So classically or quantum.
Yeah.
But the quantum or post-quantum might take fewer states.
Yep.
What is the criteria, which of the representations the neural net learns? Does it learn the one with fewer states?
Yeah, that's a great question. I think we just haven't done the experiments. We should. I think if there aren't enough dimensions in the model, it would probably be forced to get a certain level of loss, would be forced to do the simpler one. But if there's room to accommodate both, then I'm not sure what it ends up learning. Yeah. Yeah.
So the block sphere is like the sphere. It's like, what does this picture look like in 3D?
Like,
are they all
this process actually was kind of designed on purpose to just be a two-dimensional slice of the block sphere. So all belief states happen to actually live on this 2D slice.
Okay.
We could also concoct a process that lives genuinely in the 3 dimensions.
If you start off that grade zone, what's very interesting for you to consider?
Yeah, you'll like exponentially.
You never see symbols on the y-axis.
Yeah, that's right. Yeah. So, okay, so yeah.
So this belief geometry is really the support of this dynamic update, Riechers updating. You see also evidence that the dynamics as you learn data are the same as theory.
You're saying not just the static thing, but the actual dynamics of the transformation. Yeah, so we've looked into that stuff a little bit, like in the last part I was talking about with the constrained belief updating. You can see kind of what's the algorithm for that. In general, I think there's still a lot of work to do on that. People are talking a lot these days on, SLT people are talking about weight space instead of activation space, and also there's the parameter decomposition. So I think this stuff, it does imply something about the weights, but we basically haven't worked out in detail like what it means for the transformation itself.
I think I was looking at something.
Oh, yes.
More because I mean this in this next state presentation, or as you see more data, your data is
yeah.
And so it's a dynamic on this.
Yeah, there's a dynamic
space.
exactly. Yeah.
And is the dynamic on this space the theoretical one?
Oh yeah, I mean it's faithful to that. Like if you move through context positions, indeed it's faithful to that.
It's not just the support of this. It's not just the fractal. It's the dynamic on the fractal.
Yeah, that's right. Yeah, if you actually move through context position, it's faithful to moving around in the correct way. Yeah. Yeah.
So in this example specifically, what's the data generating process?
I think Tom mentioned it, but it's in. I'd suggest either going to the paper. We can talk through it earlier.
Okay.
Mm-hmm.
Sure.
But you can think about it. You can think about it like you have a qubit, like the simplest possible quantum system you have,
Right.
and then you bring in, you can think about it this way. So you have a single qubit, that's your memory, and then you bring in, more, then you bring in more ancillary qubits, and then you do a projective measurement. Then those guys unitarily evolve jointly, and then you do a projective measurement on that thing.
Okay,
And that measurement outcome is the token.
Okay, so okay, I think the thing that was most helpful for me is like state space that is actually a qubit or several qubits, and it's like not very surprising that the quantum version is good for a quantum system. And
Yeah, but like, but when we feed tokens to
non-quantum situations too, that are like
yeah, I mean when we feed tokens to the neural network, it doesn't know like that tokens are coming from like a quantum model or classical model. Right? It just sees tokens.
So is there like a non-quantum model that
well, in a way, no. Like if there is a quantum representation, then there is a quantum generator. But there's also, like I was alluding to, like even linear transformations on a latent space that are beyond this, and there's sort of. I think in the interest of time, I'm gonna move on to the last bit because then there's Alec has his talk shortly.
Oh, I was just gonna say in terms of the quantum advantage, another way to understand this is, the state of a quantum system is encoded in a matrix of the dimension that you're in over space, whereas classical system is encoded in that. But what you have here is a very high-dimensional machine that's reproducing the data. Right? So for this qubit, you have two pure states that are forming bases. The object itself is three-dimensional, blocks. And so you have at least 3 dimensions in your residual stream holding this information. So you're not necessarily getting an advantage over quantum machines. You're just encoding at additional dimensions.
Yeah, I wouldn't say you're getting an advantage over quantum machines. I mean, there's definitely an advantage over a classical representation because the minimal classical representation of this process has infinitely many dimensions.
Infinitely many quantum states or infinitely many?
Hidden states in the minimal generator. Yeah. So, all right. So let me just kind of wrap up here by looking ahead at. So we've been very excited about all these different projects. They've been, kind of in a toyous setting, but it tells us that there's like real understanding and science that can be had. So Adam and I have been thinking a lot about, well, okay, how do we structure our organization to like have real world impact? And so some of that will be continuing to build out some of the fundamental theory, and some of it, like I said at the beginning, we have kind of line of sight to success and engaging to real, interpretability of frontier models. So part of this hinges on this new theoretical part of factored belief representations, which I didn't talk about. Hopefully Henry gives a talk on that sometime this week. But the idea is that sometimes you have things in the world that are effectively independent, and if you naively extrapolated our story, it would be in like some huge high-dimensional simplex, but actually the model could kind of factor this and do simplices in parallel. Well, also, even if it's not independent, if you have just like conditional dependence between different beliefs, you could also do this factoring. And so this seems, our preliminary experiments are showing that, yeah, indeed, the model's only taking that smaller number of dimensions. It even seems to be giving the type of geometric representation that we anticipate. So this is also giving us some courage then to say, you know what, I bet we can discover these belief geometries in LLMs that if we had to figure out the whole thing at once, it'd be very intimidating. But there's probably at least parts of understanding that are, again, either independent or that there's just like this conditional dependence. So there's probably some low-dimensional subspace in the activations of LLMs where we can find this type of belief geometry. So maybe we end up, leveraging SAEs or something else to find that, which also kind of brings us to this other point of SAEs, sparse autoencoders, transcoders, things like that are pretty prominent, but they're like really not that well motivated, but they're kind of the best thing we've had. So there's something here about like how do we benchmark SAEs to say like what types of correlational structures should they be good at? And so once we kind of strongman that, we can also say, well, which sorts of correlational structures should they fail to detect? People talk about like dark matter of SAEs, but we should be able to have some more principled understanding of when they work, when they don't, and with that, what should we make instead? So something like, I see it as quite short-term thing that we can do for providing interpretability tools that I think hopefully would be a service to the community. And then there's this kind of broader vision that we have some simple experiments we're looking at and are quite interested in. How universal are representations? Like, do all intelligent, like sufficiently intelligent things, do they come to represent the world in a similar way? There's some talk of like this Platonic representation hypothesis. There's different flavors of that. Is it that we're representing the world in the same way, which kind of conceptual alignment you might think is prerequisite to other types of like value alignment. So it'd be good if we could even communicate well. And if there are fundamentally like distinct but incompatible ways of representing the world, is that bad? Like, can one intelligence ever kind of help the intelligence to refactor their beliefs to come to something like a shared understanding? So I think this is like a very large project with some straightforward experiments, but also some like quite high-level ideas, which are quite interesting. There's all sorts of more exploratory efforts that I think are really important, but it's not totally clear what the experiments look like that get us to the answer. So these are not less important, but more exploratory, looking at the training dynamics. Yasmina might end up giving a talk on some of the stuff she's been looking at with rate distortion and kind of these bumps in the training loss on different stochastic processes. How does the belief geometry change if you're fine-tuning or doing reinforcement learning on chain of thought? How does the model leverage the belief geometry it's inherited from pre-training? We had a math scholar, Jake Ward, who was looking at kind of effectively some aspect of this, and I think we'd like to look at that more explicitly in our framework. We're also looking to basically break our understanding as much as we can. We're not here to defend computational mechanics. We're here to use it if it's useful and to show where it breaks down so we can move ahead and figure out the real thing. I think Franz will maybe give a talk on one aspect of this, which Franz has been doing some cool work where he's finding effectively counters, like what you'd have for push-down automata, that maybe just a single dimension in the residual stream is sufficient for a model to be able to do that. So that also changes our picture. I think there's all sorts of even kind of like one-off projects that could be done. Like Alec was saying, well, what if you have more layers? If you have constrained belief updates for, say, the random running XOR, or if you have different types of positional embedding rope or whatever. So there's like all sorts of kind of micro stuff too that would help us to refine what's going on in these models. And we're optimistic that this all kind of plays into an agenda that has real impact. So we're excited to kind of scale our mission and like also shape things around projects where we're hoping to have kind of teams working towards this kind of level of success that would. I care a lot about AI safety, so hopefully that would actually engage with understanding these things. If nothing else, it will, I hope, elevate the conversation that's had among technologists and also the society. What are these things? Are they just tools? I think clearly not, but it'd be really nice to be able to be on the same footing, to have facts to talk to each other instead of opinions. So that's kind of my hope, and I'm grateful for all you guys being here and being part of this journey. Very happy to talk more this week, and I think I'll leave it at that.